All right, good afternoon, everyone. My name is Damon Barnes. I am the Director of Technical Marketing at the Bluetooth SIG. Today, I'm going to take you through an overview of the Bluetooth High Data Throughput feature. I'm going to cover a couple of topics before that. We'll get into some introductory information on the Bluetooth SIG itself and our global ecosystem. Then I'll also touch on some of the big four of major upcoming Bluetooth features that you should be aware of course, including high data throughput. And then after that, we'll get into a technical overview or introduction of the HDT feature. So let's get started. All right, so Bluetooth technology. It's more than, I would say, your average wireless standard. The standard itself, it's a full stack from the radio layer, as you know, all the way up to the device or application layer. And then the SIG, as a company, we operate a little bit differently than other standards development organizations. We're this one-stop shop for all things standards development, of course, but then we also handle certification or qualification, if you will. We handle the licensing, cross-licensing of the Bluetooth mark to members. And then we also handle all things marketing and promotion, where our team resides, thus Alfredo and my participation today. However, I think our biggest asset is probably you all, this global community of Bluetooth developers. And that leads me into, this group of developers, or community, I should say, consists of some of the world's most inventive companies and minds across the globe. And we're all collaborating to fulfill this essential need to connect, right? And so together, we work together to advance, protect, and promote Bluetooth technology. The rest of my talk today is going to be focused on the advancement of Bluetooth through the innovation that our members have come up with for Bluetooth High Data Throughput. So with that, let's now pivot to the big four of major upcoming enhancements. But before I start to speak on those just a little bit more, I should say that at the SIG, there are more than 50 active specification development projects in process at any given time. And so these are the big four, of course. You've already heard about ultra-low latency HID over the last hour. I'm going to get into high data throughput, a minute or two on these two on the right-hand side of the slide. High resolution and lossless audio. This is going to be the lead application or use case, rather, for HDT. HDT is a critical building block to enable high resolution and lossless audio. We're looking at trying to get that out the door toward the end of the year, maybe early 2027. And then the higher bands project, as you see here to the right side of the slide, this is where we're working to enable Bluetooth LE operation in higher mid-band spectrum, targeting 5 gigahertz and 6 gigahertz unlicensed. We'll enable 5 gigahertz first, and that's targeting 2027. So now let's start to examine HDT. So Bluetooth High Data Throughput. This project is going to enable a new feature that's going to be fundamental to creating a whole new generation of Bluetooth solutions. We're going to have new silicon. We're going to have more advanced software stacks. And of course, Bluetooth in-use products, they're going to gain new and enhanced capabilities thanks to higher data throughput. Out of the gate, of course, HDT is going to increase the max supported bit rate up to 7.5 megabits per second. That's going to help Bluetooth devices meet the increasing data demands in the ecosystem. Then you're going to see that there are going to be a number of improvements to overall wireless performance, and that's going to benefit existing applications and use cases. And I mentioned it, HDT is going to also enable or allow Bluetooth technology to standardize new use cases like high resolution and lossless audio, like I said. So with that introduction given, let's now take a look at some of the technological benefits that HDT is going to bring. Okay, so out of the gate, like I said, HDT is going to enable faster data transfers thanks to the higher bit rates, right? That's going to be nearly quadrupled compared to today's max achievable bit rate with the 2M PHY. The higher data or faster data transfer is going to be enabled primarily by adding support for higher order modulations schemes. That's going to allow us to encode more bits into every symbol that we're transferring. HDT is going to also increase capacity, right? High data throughput, nearly 4x as well. You're going to see new packet formats, lower duty cycles, and we're going to have the ability to fit multiple lower duty cycle links in a given airtime slot. Thus, greater overall spectral efficiency is going to be achieved when you combine all of the above. HDT is going to improve performance, and it's going to do so without sacrificing energy consumption. It's going to improve it, actually, or give us a couple options too, I should say. The new packet formats that I'm going to introduce in subsequent slides, they're going to enable lower duty cycles. That's going to allow for more efficient use of the radio, leading to better overall energy efficiency. Also, these new packet formats, they're going to allow us to divide our payloads into these blocks that I'll describe shortly. That's going to allow for the optimization of retransmissions when data gets corrupted. That's going to also give us the option to improve energy efficiency. And then lastly, HDT is going to enhance overall wireless communication reliability, and it's going to do so in a few ways. Number one, we're going to implement these radio features that are going to improve sensitivity. We're going to be able to increase resilience in challenging RF environments like multipath and when there's fading. And then the better overall wireless coexistence as well is going to be able to achieve. HDT is going to support forward error correction across the board at all bit rates. There's also going to be support for rate adaptability. That's going to enable these Bluetooth devices to respond better when there are degraded channel conditions. So with that summary of benefits given, let's take a look at how we're going to be able to achieve some of these benefits by a brief technical overview of some key aspects of the HDT feature. All right, before we get into all of the detail, let's take a quick look at areas of the Bluetooth stack, abstracted stack, where updates are going to be made to the core specification. If we start at the bottom of the stack, the physical layer, there's going to be a new HDT PHY. We'll look at that on the next slide. There's going to be a number of updates to the link layer. We'll step through in a moment the new packet structure and packet formats for HDT. There's going to be new procedures for HDT configuration and PHY updating. And there's going to be a new feature for encryption key scheduling that I'll take you through at a high level as well. If we move up the stack to the host controller interface, there's going to be new commands to set HDT parameters right, read payload sizes, enable testing, and the like. And then there's going to be new events to report HDT rates, encryption activities, and just to name a couple. And then if we look at the host part of the stack, the top half, so there it's kind of working. There's going to be a number of minor updates throughout the host, but that's not going to be the focus of today's presentation. We'll get into those as we get closer to HDT adoption. So now let's turn to the PHY. So I mentioned it, there's going to be one new PHY. This PHY is going to support 5 bit rates, 2, 3, 4, 6, and 7.5 megabits per second. All of them are going to operate with a symbol rate of 2 megasymbols per second. I mentioned higher order modulations. We're adding support for 3 new modulation schemes. That's Pi 4 QPSK, 8 PSK, and 16 QAM. There's going to be support for coherent detection. That's going to help enable phase and frequency synchronization between transmit and receive, and that's going to help us reduce the probability of errors. The diagrams that you can see on the slide, those illustrate the symbol constellations for each modulation scheme that are used by HDT. HDT, like I said, is going to support forward error correction across the board, right? And that's going to be based on convolutional coding with a half coding rate. There's also support for puncturing. That's to enable higher coding rates in the payload zones that we'll look at in just a moment. So now if we take a step back, we have a comparison here on this slide that shows the existing PHYs and the LE HDT PHY. Let me make a few call-outs here, some more obvious than others. So HDT, as you can see, the lowest bit rate is going to be the maximum supported bit rate, of course, with the LE2M PHY. Right. All of the existing PHYs are based on GFSK modulation. You'll see us refer to those or hear us refer to those as GFSK PHYs as a collective sum going forward. Note the sensitivity figures too. There's better sensitivity at 2M with HDT than there is the existing LE2M PHY, but do keep in mind that that's different. We're comparing different modulations, so not exactly an apples to apples comparison. HDT, of course, is going to give you the fastest speed, the greatest capacity out of all these PHYs that you see here. But if you're looking for maximum range, LE coded is still going to be your best choice there. So now let's pivot to the packets. Okay, so there's a whole new HDT or a whole new packet structure to enable HDT. As you can see on the diagram on the slide, there's the preamble, control header, PDU zone, payload zone, and CTE. CTE stands for constant tone extension, in case you're curious or unaware. That's for the direction finding feature if you're looking to use that with HDT. So the preamble and control header, those are going to be present for all HDT packets. Then you have the PDU header zone, payload zone, and CTE. Those are going to be optional depending on the packet format and, of course, if you need direction finding. One key feature that we'll start to examine throughout the next couple of slides is that with HDT packets, you have the ability to divide your payload zone into these blocks. And like I said, we'll talk about that shortly. Now let's take a quick look and go through the different zones of the packet structure with HDT. So on the preamble, that's going to consist of a series of short and long training sequences. The short sequences, those are going to be used for initial calibration and for timing and frequency acquisition. That's on the receiver side. Then these long sequences, those are going to allow for more accurate parameter estimation, and they're going to enable coherent detection and also channel estimation. So all of that, which is going to help improve sensitivity and performance in challenging RF environments like multipath. Then on the control header, it's going to define fields that specify things like physical channel address, indicators for packet format and data rate, PDU header, and the like. And then speaking of the PDU header, that's going to convey information related to packet type like transport, link IDs, payload links, presence of CTE or not, and then receive acknowledgments as well. A key point to call out here is since each HDT packet signals its data rate or has the ability to signal its data rate, the transmitting device, it's going to be able to change its rate literally on a packet-by-packet basis, which is really nice. And that's going to allow for adjustments based on the channel over-the-air quality, even before the retransmission of a packet. So to examine the payload zone a little bit more closely, let's step through a couple of slides to get into that explanation. So on this slide, let's first focus on the top half of the slide, the short format packet. It's going to be used for synchronization between devices and then also for acknowledgments. The packet, it's going to contain, like you see highlighted there, a preamble and control header only. That's going to help reduce airtime when there's no data to transmit. Also, it can be used when you only need to acknowledge consecutive whole payloads. Now if we focus our attention to the second half, or the bottom half rather, of the slide, packet format 0, which you'll see referred to as PF0. This packet format contains a single payload block with a message integrity check, which you see called out as MIC there. The MIC, it's only going to be present if the connection is encrypted and there's data to be transmitted. If there's no data, there's no payload zone. And then that CRC, which is the cycle redundancy check, that's there for error detection. It's going to be calculated based on the sum of the entire PDU header, payload block, and the MIC. And then a note on the mix, those are going to be present when there are encrypted connections. Might be ACL, could be connected isochronous stream, or broadcast isochronous stream. All three of those transports are applicable. So now the third packet format, called packet format 1. This one is the most complex and also can deliver the most benefits and highest throughput. And I'm going to describe it through a series of animations here. Let's see how this works. So packet format 1, or PF1, it supports up to 4 payloads, including a MIC if there's encryption. The payload size is 8175 octets, in case you're curious. Each payload plus MIC, it can be divided, or it's going to be divided into blocks, 1 through 16, kind of like you see illustrated there. The blocks are the same size, but the size of each payload may be different. The cycle redundancy check for error detection, like I said, is calculated for each block. And then this payload zone is going to be split into intervals with a fixed number of symbols, and that's called the phi interval symbol streams. All the phi intervals are the same size except for the last one, which can be shorter. Build that out. Then each phi interval is followed by a terminating symbol sequence, which you see denoted as TERM, or term. The terminating symbol sequences are followed by a phi interval training sequence denoted as pits on the slide, except for the last phi interval, as you can see. The phi interval training sequence is used for data-aided tracking of phase and /OR channels. And then a couple notes here. So a packet, it can be constructed with multiple short transmission blocks, each protected by its CRC, as you can see. This is effective for mitigating the impact of interference, and it's efficient since you only need to retransmit the failed blocks. Also, you can selectively acknowledge part of a payload without having to acknowledge all of it. Each block can be acknowledged separately. This means that damage to one block doesn't necessarily mean the other transmitted blocks can't be used. Lastly, you also don't need to transmit all the blocks in one packet. You can send, say, 4 blocks at a time and then leave space for other traffic in between the packets, which is really nice. A note, though, or caveat, if you will. The blocks, they do add overhead. So you have your header and your CRC for each block, right? And then you have added link layer complexity with segment and reorder and reassembly of the blocks. So that's something to keep in mind. And so speaking of, so I know I've taken you through some information on all 3 of these new packet formats. This slide summarizes the 3 packet formats that we're bringing forth with HDT. So you have the short format packet. That's going to be useful for, like I said, synchronization and for acknowledgments. And advantages of it, it can reduce error time when there's no payload or no data to transmit, and also when there's only consecutive whole payloads that need to be acknowledged. And then packet format 0, max payload of 494 octets. I think I failed to mention that previously. So you're definitely going to see an increase in throughput with packet format 0. And so if your application can function or operate with that max payload size, that might be the most advantageous packet format. It's going to be simpler to implement with lower overhead than when compared to packet format 1. And then packet format 1, obviously the largest, most robust packet format, highest throughput, best efficiency, best robustness of all 3 packet formats. And then, a few summary notes on that packet format that I just mentioned. Up to 4 payloads in a packet. That also allows you to divide the payloads into blocks, selective acknowledgments, right, and the phi intervals and phase tracking that I mentioned. So that's a breakdown of the packet formats that we introduced with HDT. So now there are some updates to encryption in the core specification to enable HDT operation. So there are not any changes to the existing supported security algorithms. However, we do increase or introduce support for longer mix sizes with the GFSK PHYs, LE, of course, uses 32-bit mix sizes. With HDT, we're adding support for 64 and 128. And then there's this new encryption key schedule feature, and that's going to allow us to change the key, the mix size, and the PHY all simultaneously without disconnecting or restarting an encryption procedure. And then number 4 on this slide, there is a new opportunistic encryption feature as well. That's going to allow at the link layer to enable encryption in the absence of the long-term key or pairing. So that's a quick high-level summary of encryption enhancements within the core specification that are going to come forth to enable HDT and allow it to function at a very high level. All right, so now that kind of concludes my high-level technical overview of HDT. But if we talk about kind of how it operates at a high level as well, I would describe it something as follows. So first, what's going to happen? The connections, they're going to be established via one of the existing GFSK PHYs. The GFSK connection may or may not be encrypted. It's up to the implementer. The devices will then exchange HTTP features and configuration parameters. Then there's going to be this switch to the HTTP PHY. That's going to happen via the PHY update procedure. And so either the central or the peripheral device can make that request to change to the HTTP PHY. Once the HTTP connection events are in progress, HTTP, like I said, can rate adapt up or down based on the link performance or quality. On the transmit side, a couple of details to call out. Each packet is going to be signaling its data rate in the control header. That transmitting device can then change rates on a packet-by-packet basis to adjust for the channel quality, just to reemphasize that point. And then on the receive side, that optional link quality feature in the PDU header allows a receiving device to feed back RSSI, SNR of those received packets, and this is going to allow that transmitting side to adjust and choose the best available HTTP parameters like data rate, block size, and the like. And that's a high-level summary of HTTP operation. Before I can conclude, we've had this HTTP demo at CES and other events prior to that. This demo's been provided by Samsung LSI, so we tip our cap and thank them for continuing to help us promote Bluetooth technology. What I'm going to show you in this really short video is a file transfer demonstration, first using the 2M PHY and then using the HTTP PHY. We're going to run a transfer of a MP3 file. So let me start this here real quick. The first transfer using the 2M PHY does take several seconds. It looks like we're going to transfer a 2.7 megabyte file, and I believe it's going to take nearly 16 seconds. We hit about, what's that, about 1.4 megabits per second. That's application data rate. It's getting pretty close to finishing here. Yep, exactly 16 seconds for that file transfer to occur. Now we're going to switch to HTTP packet format 1 and run that same transfer. And let's see how long it takes. Done already, right at 4 seconds. So there you have it, 4x speed improvement transferring a file using HTTP compared to the existing LE 2M PHY. So with that concludes my presentation, and I would like to say thank you all for helping us create a better world through connection and continue to do so in the future. Thank you very much.